Good morning everybody. Today's session we are going to discuss about the wave motion or oscillatory motion. First of all, let us know what is motion. Motion is defined as when a body changes its position either with respect to a point of reference or with respect to time, then we say the body has undergone some motion. Motion is of three different types. One is the linear motion, secondly the circular motion, and thirdly it is the vibratory or oscillatory motion. In the linear motion, a body always travels along a straight line. In a circular motion, the body always travels along a circular path. It can be a elliptical path, a complete circle, or a part of the circle. Whereas in oscillatory or vibratory motion, the body undergoes to and fro motion or front and back motion from its mean position. Example for linear motion is a person moving along a lift or a freely falling body is an example for linear motion. Example for circular motion is a person sitting in a giant wheel going round the giant wheel is an example for circular motion, or the planets revolving round the earth is also an example for circular motion. Whereas the example for oscillatory or wave motion is the vibration of a simple pendulum, or the clocks, the hands of a clock rotating in the clock is also an example for oscillatory or vibratory motion. Now let us know what is an oscillation, a wave, and different types of motion we come across in oscillatory and wave motion. First, let us define what is a periodic motion. Any body is said to be in motion if it changes its position either with respect to a point of reference or with respect to time. That is the definition of motion. So, a periodic motion is one in which any motion repeats itself at regular intervals of time. Such type of motion we call as periodic motion. Example is the oscillation of clock pendulum. The vibration of clock pendulum repeats after every 1 second. So, it is a periodic motion. Also, a simple harmonic motion is an example for periodic motion. Next, let us know what is simple harmonic motion. So, if a particle is moving along a circumference of any circle like the hands of a clock with uniform speed, then the motion of the foot of the normal drawn from the particle onto any diameter of the circle represents simple harmonic motion. Suppose the hands of the clock is rotating, second hand is rotating. If we draw a perpendicular of that to the foot of the diameter normal from the particle onto any diameter of the circle, it represents a simple harmonic motion. Example, oscillatory motion of a pendulum, vibrating prongs of tuning fork execute simple harmonic motion. You can see in this figure the vibration of pendulum. A pendulum oscillates. V represents the velocity of the oscillation, A represents the acceleration, and the red arrow, small arrow or theta represents the displacement of the angular displacement of the simple pendulum. The dotted blue line represents the mean position of the pendulum. This is the vibrating prongs of a tuning fork. The prongs of the tuning fork vibrate to and fro motion, undergo to and fro motion. So, inward motion as well as the outward motion of the tuning fork is shown here. Now, let us derive the equations of a particle executing simple harmonic motion. So, equations of motion for a particle executing simple harmonic motion. Now, here we have a body which is moving along a circular path. AB and CD are the two diameters of the circle. The radius of the circle is represented by OP or OB, that is given as R, radius of the circle R. Now let initially the particle be at the point B. After some time, let it move to the point P. From the point P, we join the radial vector to the center of the circle, and that is represented by OP. Next, we shall draw the perpendiculars from the point P to both the diameters AB and CD, represented by PM and PN respectively. So, the angular displacement of the particle when it has moved from B to P at the center of the circle is represented as theta. So, if angle MOP is equal to theta, then angle OPN is also equal to theta, because they are alternate angles. So, that is the description of what I just now told. Let AB and CD represent two mutually perpendicular diameters of a circle of radius r and center O. Consider a particle P moving with uniform speed along the circumference of the circle. Let the angular velocity of the particle be omega. Suppose the particle starts from moving from B after t seconds. Let the angle described by the radius vector be theta radians, and m be the foot of the perpendicular drawn from P on the diameter CD. Then the particle P completes one revolution, that is, sweeps a central angle of 2 pi radians along the circumference of the circle during the same time. The foot m of the normal moves back and forth along the diameter CD of the circle, and the length or the distance of this foot is not the same at all positions, as the diameter as the normal moves back and forth along the diameter CD. The motion of M is the simple harmonic motion. The motion of M along the diameter is what we call as simple harmonic motion. Next, displacement of the simple harmonic motion. Let us derive an equation for the displacement of the simple harmonic motion. So, if we represent the points of P in the two coordinate system as x comma y, OM will be equal to y and OP will be equal to, and OM will be equal to y and PN will be equal to x. So, y is equal to OM is the displacement of M from the origin O in a time t seconds. From the right angle triangle OPM, we can define sin theta. Sin theta is defined as the opposite side by hypotenuse. The opposite side in this triangle OPM, right angle triangle OPM, is PM and the hypotenuse is OP. So, sin theta is equal to PM by OP, and we know that PM is equal to y and OP is equal to R. Therefore, y is equal to R sin theta. But if we write the angular velocity omega in terms of the angular displacement, omega is equal to theta by t. Therefore, theta is equal to omega into t. So, we get y is equal to R sin omega t as the formula for the displacement of the simple harmonic motion at any instant of time t seconds. So, y is equal to sin omega t. R sin omega t is the displacement of any particle executing simple harmonic motion at any instant of time t seconds. Differentiating the displacement of the simple harmonic motion, we get the velocity of the simple harmonic motion. So, velocity v of simple harmonic motion is d by dt of y. Differentiating r r sin omega t, we get r differentiation of sin is cos omega t, and applying the chain rule, the differentiation of omega t is omega. So, we get dy by dt is equal to r omega cos omega t, and that is the velocity of the simple harmonic motion. If we write cos omega t in terms of sin omega t, we can write omega into root of r square into 1 minus sin square omega t, because cos omega t is root of 1 minus sin square omega t. We are taking the r into the root sign, so that we can write r square sin square omega t as y square. So, simplifying, we get the velocity of the simple harmonic motion v is equal to omega root r square minus y square. Now, in this equation, if we put y is equal to 0, then v is equal to r omega. If we put y is equal to plus or minus r, then v is equal to 0. So, velocity is maximum at the mean position O and decreases as the particle moves away from O on either sides. So, at C or D, the velocity vanishes. Next, let us see what is the acceleration of simple harmonic motion. We know velocity of simple harmonic motion is v is equal to r omega cos omega t. Acceleration is the rate of change of velocity, or we get it in terms of differentiation. If we write, acceleration is d by dt of v. So, that is equal to differentiation of r omega is r omega, because they are constants. Differentiation of cos omega t is minus sin omega t, and applying the chain rule again, differentiation of omega t is omega into 1. Therefore, acceleration A is equal to dv by dt, that is equal to minus omega square sin omega t into r. Replacing r sin omega t as y, we get acceleration is equal to minus omega squared y, minus omega squared y, where omega is a constant. Hence, we can write the acceleration is directly proportional to the displacement y. A is directly proportional to y. As the velocity has a negative sign, the velocity increases in a direction opposite to the motion of a particle. Hence, the simple harmonic motion can also be defined as that type of periodic motion in which acceleration is proportional to the displacement, but is directed towards the mean position. There is a correction there, as the acceleration has a negative sign, the acceleration increases in a direction opposite to the motion of a particle. Hence, the simple harmonic motion can also be defined as that periodic motion in which acceleration is directly proportional to the displacement. Now, let us calculate the period of simple harmonic motion, that is the time taken by the body to complete one simple harmonic motion, one complete oscillation. So, the period of any vibrating body is defined as the time required to complete one oscillation. So, when P completes one revolution, it sweeps a central angle of 2 pi radians at the center. So, M completes an oscillation when the point P rotates through an angle of 2 pi radians. Time required for the P to complete one revolution, if you say it is the time period capital T, that is equal to 1 second into 2 pi by omega, because we know omega is equal to angular displacement by time. So, time is equal to angular displacement by omega. So, we get it as 2 pi by omega seconds. So, that time period of simple harmonic motion is 2 pi by omega, where omega is the angular velocity of the particle executing simple harmonic motion. Next, let us define what is the frequency of a particle executing simple harmonic motion and also get an equation to calculate the frequency of simple harmonic motion. The number of oscillations completed in 1 second is called as frequency, and the number of oscillations per second of the particle executing simple harmonic motion is called the frequency of a particle executing simple harmonic motion. So, if n is the frequency of the particle executing simple harmonic motion, then its period t is equal to 1 by n, that is equal to 1 by nth of a second. Therefore, time period t is equal to 1 by n or n is equal to 1 by t. We know t is equal to 2 pi by omega. So, we get the frequency n is equal to omega by 2 pi. The SI unit for frequency is hertz, and the CGS we can even write it as cycles per second. The dimensions are m0, L0, t minus 1. Next, let us see what is a vibratory motion or an oscillatory motion. The examples of some of the examples of the vibratory motion or oscillatory motion is, as I told earlier, the motion of pendulum bob, the clock pendulum or simple pendulum it might be, the motion of prongs of a tuning fork, etc. are some examples executing vibratory motion or oscillatory motion. In the example of the pendulum, I told the dotted lines, the blue dotted lines represent the mean position. So, the movement of the pendulum in one direction we call as to motion, and the momentum of the pendulum in the opposite direction from the dotted blue lines we call it as fro motion. So, when a body is executing oscillatory or vibratory motion, the body executes one to motion and one fro motion. So, one complete to and fro motion of a body is called as an oscillation or a vibration. So, the resting position of the body before starting its vibration is called mean position, and the to and fro motion of a body about its mean position is called a vibration or vibratory motion. So, when a body starts vibrating from its mean position, gradually its distance from the position called displacement increases and reaches the maximum value. Then the particle starts coming back and reaches its mean position. This is called the to motion or forward motion. Next, the body moves in the opposite direction in the same manner, reaches maximum position and comes back to mean position. This is called fro motion or backward motion. One to and fro motion constitutes one vibration or one cycle. The displacement of the body executing oscillatory motion or vibratory motion, y, it is defined as the normal distance moved by the vibrating body from its mean position at any instant. The normal distance moved by the vibrating body from its mean position at any instant is called the displacement. The maximum displacement of the vibrating body from its mean position on either side is called as amplitude, and it is represented as r. Both displacement and amplitude are measured in terms of meters. The dimensional formula remains as m0, L1, T0 for both displacement as well as for amplitude. The frequency of a vibrating body is defined as the number of vibrations made in 1 second, or it is the number of oscillations completed in 1 second. It is expressed in hertz or cycle per second. The dimensional formulas is m0 L0 t minus 1. The time period of an vibratory motion is defined as the time taken to complete one oscillation or one vibration, and it is expressed in second. The dimensional formula for time period is m0 L0 t plus 1. Next, let us derive a relation between the period and frequency of a vibrating body. We know that time taken to complete n vibrations is equal to 1 second. So, the time taken to complete one vibration will be equal to 1 by nth of a second, 1 by nth of a second, and we know the time taken to complete one vibration is the time period t. Hence, the time period t is equal to 1 by n or 1 by f, because the symbol for frequency can either be n or f. So, the time period t is equal to 1 by n or 1 by f. That is the relationship between the time period and frequency. So, the product of the time period and frequency will always be equal to 1 second. This is the graph which shows the relationship between period and frequency. So, we have plotted a graph of displacement y versus time t. So, the time taken to complete one cycle, that is represented as the time period t. The number of oscillations completed in 1 second is called the frequency. So, using this graph we can show that the time period t is equal to 1 by n or 1 by f. Next, let us know what we actually mean by wave motion. See, if we take a stone, drop it into a still water pond, it can be observed that there are quick expanding circles from the point where the stone was dropped, produced in all directions. But we also observe that if we carefully observe that, we can also note down that water does not move. Instead, only the disturbance created on quiet water surface moves away in all surrounding directions in the form of regular wave along water surface. But the water molecules will just move up and down about their mean position. So, the same thing if we see in a spiral spring of regular pitch, that is, if it is tightly turned or loosely turned, the complete spring should be of regular pitch. The space between the turnings must be same. So, when few turns at one end are compressed and released, the disturbance travel along the spring towards the other end, but the turns will be vibrating at their mean position. The next example, if we see, if we take a rope fixed to a rigid point, other end is suddenly moved up and down, then the disturbance created at the free end of the rope travels along the rope in the form of wave without actual movement of the rope. From the above examples, we observe that when a disturbance is created in a medium, the transmission of disturbance takes place from one molecule of one region to the other, but in no case there is no transmission of molecules of the medium. This type of motion is called wave motion. So, we define wave motion as the transmission of disturbance without actual transfer of medium. The transmission of disturbance without actual transfer of medium particles is called wave motion. During the wave motion, the particles of the medium do not travel, but they just oscillate about their mean positions. Wave acts as a carrier of energy, and in wave motion, energy is transferred from one part of the medium to the other part. Generally, Waves are classified into two groups or two categories, namely the mechanical waves and the non-mechanical waves or electromagnetic waves. The mechanical waves are the one which require a medium for their propagation, whereas the non-mechanical waves are the one which do not require a medium for their propagation. So, a material medium is necessary for the propagation of waves, then we call such waves as mechanical waves. Example for mechanical waves are waves produced on water surface by dropping a stone into it, waves produced in the spiral spring by compressing certain turns at one end, waves produced in the rope by moving one end suddenly up and down with the other end fixed at the rigid support. The non-mechanical waves are one which do not require the material medium for their propagation. The non-mechanical waves or electromagnetic waves can even travel in vacuum. They can travel through vacuum. Examples for non-mechanical or electromagnetic waves are light waves, heat waves, radio waves, infrared rays, microwaves, etc., visible light, etc. This is a graphical representation of the wave motion. It is a graph of displacement versus time. Again, there is a mistake done there, distance. It is not the distance, it is time, displacement versus time. And the distance between two crusts, the maximum amplitudes of on the wave, or the distance between the two troughs, the minimum amplitude on the wave, we call it as the wavelength, and it is represented by lambda. It is measured in terms of meters. The dimensional formula for wavelength remains as m0 L1 T0. Now, let us look into some of the definitions related to wave motion. First, let us define what we mean by wave period. The wave period is again has the usual symbol capital T. It is measured in terms of seconds. The period of a wave is defined as the time taken by a particle of the medium to complete one oscillation. I repeat, the time taken by a particle of the medium to complete one oscillation is called the time period or wave period. The wave frequency. The next definition is the wave frequency. So, the frequency of the wave is defined as the number of waves moving through a point in 1 second, or the number of oscillations made by the particle of the medium in 1 second is also called as wave frequency, denoted as N, measured in hertz. Next definition is the wave amplitude. The amplitude of the wave is the maximum displacement of the particle of the medium from its mean position. So, when we drop a stone into a still water, the water molecules will vibrate up and down, to and fro. So, the maximum displacement of these water particles from its mean position on either side is what we call as wave amplitude, and it is represented as R. It is measured in meters. The next definition is the wave velocity. The velocity of a wave is the distance travelled by the wave in the medium in 1 second. That is, the velocity of a wave or the wave velocity is the distance travelled by the wave in the medium in 1 second. The velocity, wave velocity is measured in meters per second. The dimensional formulas remain as m0 L1 T minus 1. The next definition is the wavelength, wavelength of a wave. Wavelength is defined as the distance between two consecutive particles of the medium which are in the same condition of vibration, or the distance between the two particles which are in phase is also called as wavelength, or we also define the wavelength as the distance between two consecutive crusts or troughs, or we even define the wavelength as the distance between two consecutive compressions or rarefactions in a longitudinal wave. So, there are various definitions for the wavelength. General definition I would like to tell is the wavelength is the distance between two consecutive particles of the medium which are in the same condition of vibration. Suppose one particle is attained maximum amplitude, if another particle has also attained maximum amplitude, the distance between these two particles with maximum amplitude, we call it as the wavelength. The next, let us derive a relation between the wave velocity, frequency and wavelength, that is V, N and lambda. According to the definition, the wave velocity is defined as the distance travelled by the particle in 1 second. So, the distance travelled by the particle in a time period t seconds is nothing but the wavelength. So, the velocity is wavelength by time period, or V is equal to n lambda, because 1 by t is equal to n. We have already shown that the time period is the reciprocal of frequency, or the frequency is the reciprocal of time period. So, substituting 1 by t as n, we get the velocity, wave velocity V is equal to n into lambda, where n is the wave frequency and lambda is the wavelength. So, that is the relationship between wave velocity, wave frequency and wavelength. V is equal to n lambda. Next, the waves are generally classified into two types, mechanical waves and non-mechanical waves. Further, the mechanical waves are classified into two types, that is transverse waves and longitudinal waves. Depending on the mechanism of transmission, the mechanical waves are classified into two types, transverse waves and longitudinal waves. In a wave, if the particles of the medium vibrate in the perpendicular direction to the propagation of wave, then we call such type of waves as transverse wave. For example, if we throw a stone into a quiet surface of water, the nature of disturbance produced on the water is in the form of ripples, and the ripples move in one direction, whereas the disturbance is mutually perpendicular to that, or the vibration of water particles is mutually perpendicular to the wave propagation. Such type of waves are called as transverse waves, that is the disturbance produced in the wave is mutually perpendicular to the propagation of wave. A transverse wave is represented by a sine wave which have maximum amplitudes called as crests and minimum amplitudes called as troughs. So, the distance between two consecutive crests or two consecutive troughs is called as the wavelength, represented by lambda. A longitudinal wave is one in which the disturbance as well as the wave propagation are parallel to each other, or they are in the same direction. That is, if the wave in which the particles of the medium vibrate in the same direction as the propagation of wave is called longitudinal wave. Example, the vibrating tuning fork propagates, the disturbance and the wave propagation are in the same direction. The other example for longitudinal waves is the spring of a particular pitch. If few turns at one end are compressed and released, the disturbance gets travelled throughout the spring. That is also an example for longitudinal wave. Both the disturbance as well as the wave propagation are in the same direction. Another example for longitudinal wave is a sound wave. So, a sound wave is generally, or a longitudinal wave is generally represented by compressions and rarefactions. When the molecules, when the vibrating particle moves in one direction, the molecules will get compressed. When it moves in the opposite direction, the molecules will get rarefied or rarefaction will take place. So, a longitudinal wave is generally represented by compressions and rarefactions. The C represents the compression of the medium and R represents the rarefaction of the medium. So, the distance between two consecutive compressions or two consecutive rarefactions is called as the wavelength lambda. Now, let us see some differences between the transverse waves and longitudinal waves. The nature of the propagation itself differentiates the transverse wave and longitudinal wave. That is, in transverse wave, the particles of the medium vibrate in a direction perpendicular to the propagation of wave, whereas in longitudinal waves, the particles of the medium vibrate parallelly with the direction of the wave propagation. That is the first difference between transverse wave and longitudinal wave. The vibration and wave propagation are mutually perpendicular in transverse waves. The vibration and wave propagation are parallel in case of longitudinal waves. The second difference, as I told earlier, a transverse wave is represented by crests and troughs. The maximum amplitude represents crests and the minimum amplitude represents troughs, whereas a longitudinal wave is represented by compressions and rarefactions. The medium either gets compressed or rarefied. That represents a longitudinal wave. The third difference is a transverse wave can travel in solid and only at the surfaces of liquids. I repeat, the transverse waves can travel through solids and only at the surfaces of liquids, any liquid, whereas a longitudinal wave can travel either in a solid, liquid or a gas. Example for longitudinal wave is sound waves, transverse waves is water ripples or the vibration of a rope. The fourth difference between transverse wave and longitudinal wave is transverse waves can be polarized, whereas longitudinal waves cannot be polarized. Polarization is a process where we can separate out the two components of the wave, that is the vibration, particle vibration and the wave propagation can be separated out using a polarizer in case of transverse waves, as they are mutually perpendicular to each other, whereas a longitudinal wave, they cannot be separated, that is the wave propagation and the vibration of the particles cannot be separated because they are parallel to each other. Hence, longitudinal waves cannot be polarized. Those are few differences between a transverse wave and a longitudinal wave. Though both are mechanical waves, they are differentiated based on their propagation, wave propagation and the mediums through which they can propagate. Now, let us solve some problems based on the equations V is equal to n lambda and the equations of simple harmonic motion. Now, the first problem stands as a All India radio of a city broadcasts a program on a wavelength of 500 meter. If the velocity of electromagnetic wave is 3 into 10 to the power of 8 meters per second, then the frequency of the signal is dash. So, the wavelength of the broadcasting signal, wavelength of signal is given as 500 meters. The velocity with which it is broadcasted, wave velocity is 3 into 10 to the power of 8 meters per second. We are asked to calculate the frequency of the signal. We know the velocity, wave velocity V is equal to n lambda. So, we get n is equal to V by lambda. Substituting, we get a frequency of 600 hertz. So, the signal is transmitted with a frequency of 600 hertz, wavelength 500 meter and wave velocity 3 into 10 to the power of 8 meters per second. The second problem, a particle in simple harmonic motion has an amplitude of 0.5 meter and angular velocity of 1000 SI units. The velocity of particle at a distance of 0.3 meter is dash. So, it is a particle executing simple harmonic motion. So, we will have to use the equations of simple harmonic motion, that is, we are asked to calculate the velocity of the particle executing simple harmonic motion. So, the data given to us in the problem, as we read clearly, the amplitude of simple harmonic motion, that is r is equal to 0.5 meter. The angular velocity omega is equal to 1000 SI units. Since angular velocity is angular displacement by time, angular displacement is measured in radians, time is measured in seconds. So, the angular velocity will have the SI units radian per second, and the displacement of the particle is given as 0.3 meter. So, the wave velocity V is equal to, or the velocity of simple harmonic motion is omega root r square minus y square. Substituting the data, omega is 1000, r is 0.5, y is 0.3, we get the velocity of the simple harmonic motion as 400 meters per second. Next problem, a wave of frequency 600 megahertz travels at a speed of 3 into 10 to the power of 8 meters per second. Its wavelength is dash. So, we are asked to calculate the wavelength of a frequency 600 megahertz travelling at a speed of 3 into 10 to the power of 8 meters per second. So, the data given to us is frequency n is equal to 600 megahertz, velocity, wave velocity is 3 into 10 to the power of 8 meters per second. So, what is the wavelength lambda? Now, before doing the substitutions, we have to convert this megahertz to the hertz, SI units hertz. So, 1 megahertz is nothing equal to 10 to the power of 6, mega means 10 to the power of 6. So, 600 megahertz means 600 into 10 to the power of 6 hertz. So, doing the substitutions, we get V is equal to n lambda. So, lambda is equal to V by n. V is 3 into 10 to the power of 8, frequency is 600 into 10 to the power of 6. So, we can write that 600 into 10 to the power of 6 as 6 into 10 to the power of 8, 10 to the power of 8 gets cancelled, 3 by 6 is 0.5 meter. The next problem is again based on simple harmonic motion. So, a body executing simple harmonic motion of amplitude 6 centimeter has a velocity of 60 centimeters per second. If the displacement is 3 centimeter, the angular velocity is dash. So, again we are not asked to calculate the angular velocity, instead we are asked to calculate the angular velocity omega. So, the data given to us in the problem is the amplitude r is equal to 6 centimeter, the wave velocity or the velocity of simple harmonic motion V is equal to 60 centimeter per second, and the displacement y is 3 centimeter. So, we have the formula again, V is equal to omega into root r square minus y square, but here we are asked to calculate the angular velocity. So, omega is equal to V divided by root of r square minus y square, that is equal to, substituting V is 60 centimeter per second, r is 6, y is 3. So, we get the angular velocity as 11.54 radian per second, 11.54 radian per second. The next problem, the radio wave there is a slight mistake, it is not ratio, it is radio wave. The radio wave travels at 3 into 10 to the power of 8 meters per second. So, as I told earlier, all electromagnetic waves travel with a velocity of 3 into 10 to the power of 8 meters per second. And example for electromagnetic waves I listed where radio waves, light waves, microwaves, ultraviolet rays, infrared rays, etc. So, any electromagnetic wave travels with the velocity of light, that is 3 into 10 to the power of 8 meters per second. So, the frequency of the short wave on 25 meter band is dash. So, you are asked to calculate the frequency of a short wave on a 25 meter band. So, the wavelength of the signal is given as 25 meter, the velocity is 3 into 10 to the power of 8 meters per second. Again we are asked to calculate the frequency. So, V is equal to N lambda is the formula. So, N is equal to V by lambda. V is 3 into 10 to the power of 8 and the wavelength is given as 25 meter. So, doing these substitutions we get the frequency, calculated frequency as 12 into 10 to the power of 6 hertz, 12 into 10 to the power of 6 hertz. 10 to the power of 6 is written as mega. So, we get 12 megahertz as the frequency of the radio wave transmitted on a short wave of 25 meter band. Next, All India Radio of City broadcasts the program on a wavelength of 500 meter. This is a medium wave transmission, not a short wave, it is a medium wave transmission. All India Radio of a City broadcasts the program on a wavelength of 500 meter. Express this capacity of the station in terms of frequency. Assume the velocity of electromagnetic waves. As I told in the previous problem, they have not given the value of the velocity. We have to take all electromagnetic waves travel with the velocity of light, that is 3 into 10 to the power of 8 meters per second. So, the wavelength is given as 500 meter, the velocity is 3 into 10 to the power of 8 meter per second. So, again using the formula V is equal to N lambda, we are asked to calculate the wavelength, the frequency. We are asked to express the capacity of the station in terms of frequency. So, frequency is calculated as V by lambda. V is 3 into 10 to the power of 8 meters per second, wavelength lambda is 500 meters. So, we get the frequency as 600 megahertz, 600 hertz, kilohertz it should be. If we calculate, we get a power of 10 to the power of 3. So, 600 kilohertz is the frequency of the radio station. The next problem, a particle is executing simple harmonic motion with an amplitude of 0.5 meter. Find the velocity at a distance of 0.3 meter from the equilibrium position, given the angular velocity omega is equal to 1000 SI units. So, the data given to us, amplitude r is equal to 0.5 meter, the displacement y is equal to 0.3 meter, the angular velocity omega is 1000 SI units. So, the velocity of the simple harmonic motion is given by v is equal to omega root r square minus y square. So, omega is 1000, r is 0.5 meter, y is 0.3. So, substituting those values, we get the velocity of simple harmonic motion with an amplitude 0.5 meter, velocity 0.3 meter and angular velocity 1000 SI units as 400 meters per second. 400 meters per second. The next problem, a wave of frequency 600 megahertz travels at a speed of 3 into 10 to the power of 8 meters per second. Calculate its wavelength and frequency of same type of wave whose wavelength is 40 meters. So, a same type of wave travels with the velocity 3 into 10 to the power of 8 meters per second. So, we are asked to calculate the frequency when the wavelength changes from earlier to 40 meters. So, if we assume the frequency N1 as 600 megahertz, V is 3 into 10 to the power of 8 meters per second, lambda 1 we are asked to calculate, that is the wavelength, and then what will be the frequency when the wavelength changes to 40 meter, that is our problem. So, we have two stages of the problem. One stage we are asked to calculate the wavelength, and the next stage we are asked to calculate the frequency. So, we know V is equal to N1 into lambda 1. So, lambda 1 is equal to V by N1. Substituting the values of velocity and N1, we get the wavelength as 0.5 meter. Since as I told, the wave is of same type, the velocity remains same. So, it also travels with the velocity of 3 into 10 to the power of 8 meter per second. So, again using the formula, V is equal to N2 lambda 2, N2 is equal to V by lambda 2. The lambda 2 is given as 40 meters and the velocity is 3 into 10 to the power of 8 meter per second. So, substituting these values of velocity and lambda 2, we get the frequency is equal to 7.5 megahertz. So, for the case 1, the wavelength is 0.5 meter, and for the case 2, when the wavelength becomes 40 meter, the frequency becomes 7.5 megahertz. So, we can see that the frequency and the wavelength are inversely proportional. As the frequency increases, the wavelength will decrease, or as the wavelength increases, the frequency will decrease. That can be seen here. When the frequency is 600 megahertz, the wavelength is 0.5 meter. When the wavelength is 40 meters, the wavelength is 7.5 megahertz. The frequency has decreased. So, the frequency and wavelength are inversely proportional. So, the product of frequency and wavelength for an electromagnetic wave will always remain a constant, and that is 3 into 10 to the power of 8 meters per second. So, frequency and wavelength are inversely proportional. The velocity of electromagnetic wave will always remain a constant, because N2 decreases, lambda 2 will increase. So, the product of N and lambda will remain a constant at 3 into 10 to the power of 8 meters per second. The next problem, a body executing simple harmonic motion of amplitude 6 centimeter has a velocity of 60 centimeter per second. When its displacement is 3 centimeter, determine the period. So, here we are asked to calculate the time period of the simple harmonic motion. So, the data given to us is the amplitude r is equal to 6 centimeter, the velocity is 60 centimeter per second, the displacement y is equal to 3 centimeter, time period is what? First, the formula for time period of simple harmonic motion, t is equal to 2 pi by omega. We know the pi value is 3.142, but we do not know the angular velocity. So, let us first calculate the angular velocity from the formula. V is equal to omega root r square minus y square. So, omega, the angular velocity, is equal to V by root of r square minus y square, that is equal to 60 by root 6 square minus 3 square. So, we get the angular velocity as 11.54 radians per second. So, substituting that value in the time period 2 pi by omega, we get the time period of the simple harmonic motion as 0.54 seconds. So, the period of simple harmonic motion is 0.54 second. Thank you.